Okay, time up, sir.
Okay.
We'll go. Right.
Hello everyone, this is Professor Ashish Chaudhary from IIIT Bangalore. Okay, so welcome to the first live session, live interactive session for the Discrete Maths course. So we are already in the week 5 of the course, and I'm here to take questions from you. If you have any questions to ask, of course we have the discussion forum, right, where I am actually responding. So the TAs are not handling the discussion forum. I only am handling the discussion forum. So I already saw some interesting questions there, and I've replied to them. So let me start by summarizing what we have done till now. So the discrete mathematics, it's a very important course in computer science. It's one of the fundamental courses like algorithms, data structures, theory of computation, formal languages, and automata theory. Like these courses, discrete mathematics is also one of the important courses. Uh, so many students ask this question that what exactly is discrete mathematics? What exactly the term discrete signifies here? So discrete in the discrete mathematics is basically all about uh, discussing uh, about discrete objects, objects which have well-defined boundaries. Well-defined boundaries in the sense we know where exactly the boundary starts and where exactly the boundary ends. We can clearly separate them out. Unlike your continuous objects or continuous entities like real numbers, where between every real number you can have another real number coming up. Unlike those entities, discrete objects have well-defined boundaries. And in computer science, very often we encounter discrete objects. So, for instance, graphs. Many people might be aware of the graph data structure consisting of set of nodes and set of edges. So, graph is a discrete object because the nodes have well-defined boundaries, edges have well-defined boundaries. Integers are discrete objects because between any two integers you can't find another integer suddenly, right? So they have well-defined boundaries. In the same way, the steps of the algorithms, any algorithm that you have, that constitutes a discrete objects. And since we are talking about discrete objects, a very natural question will be, can we count them? Can we enumerate some properties regarding those things? So that's why the problem of counting, how exactly we count discrete objects, that's another fundamental thing that we discuss in this course. We have not yet started our discussion on combinatorics. Very soon, in the subsequent weeks, we will start our discussion on combinatorics, namely how do we count things, because since we are talking about discrete objects, we will be interested to count them. And another important topic in discrete mathematics is that of the theory of countability, because even though integers are infinite set, since we can kind of discretize them, basically we want to enumerate some properties regarding what can we say about cardinality of the set of integers, and that's how the whole theory of countability starts, where we talk about countable sets and uncountable sets. Okay, right? So we started the course with a very basic topic of logic, propositional logic, because mathematical logic to be more precise. And logic basically gives you a set of tools based on which you derive new statements, verify whether mathematical statements are correct or not, etc., etc. We saw various kinds of logical identities. We discussed how, when do we say whether argument form is valid or invalid. An argument form will be called as valid if we can derive the conclusion based on the truth of your premises, whereas if the conclusion cannot be derived from the truth of your premises, then we cannot say that the argument form is valid. And then we saw various methods using which we can prove whether an argument form is valid or not. We have the truth table method, but we do not use truth table method because depending upon the number of variables which you may have in the statements, the truth table might become extremely large to handle. That's why we derive the validity of argument form based on various rules, various logical identities. So we saw various logical identities like De Morgan's law and modus ponens, modus tollens, etc., etc. Okay. Then we also discussed during the first 2 weeks regarding the resolution refutation, how exactly we prove whether an argument form is valid or invalid using proof by resolution refutation. Then we started discussing about the generalization of propositional logic, namely predicate logic, where we now want to uh, um, write statements, mathematical statements, not about just a single entity, but rather a set of entities or a huge population. Okay, say for instance, I want to state some property regarding the set of integers, the set of natural numbers, the set of real numbers, then I will be using predicates, right? Because I cannot write down the same statement again and again and again, right, for each and every candidate integer. So whenever we face scenarios like this, whenever we want to make a general statement regarding more than one element of a population, then we use predicate logic. And in predicate logic also we have various logical identities. We saw methods when we can say whether a given argument form involving predicates is valid or not. We have universal quantification, existential quantification. We saw how to prove a universally quantified statement, how to prove existentially quantified statements. We saw various proof methods also as part of our first couple of weeks material. Various proof methods which we encounter in computer science. We have the direct proofs, we have the indirect proofs. In the direct proof, basically all these proof methods basically deal with how to prove implications, statements of the form if then, okay, namely P implies Q. And direct proof method basically uses the fact that assuming your premise is true, you arrive at a conclusion. We also saw that there are several statements where P implies Q cannot be directly proved, so we resort to indirect proof methods. And under the indirect proof methods, we have various proof methods like proof by contrapositive, okay, proof by contradiction, and so on. We also saw how to prove existentially quantified statement. For existentially quantified statement, I can either construct a witness, show the existence of a witness, concrete witness, or I might logically argue that the witness exists, but I may not be able to write down the exact witness. So the famous the statement where we proved that there exist infinite number of primes, uh, we proved it using contradiction, but we logically argued it. Okay. In the same way, uh, we saw proof by induction. The induction, we have two different types of inductive proofs. We have the regular induction, we have the strong induction, and inductive proofs are used whenever we want to prove universally quantified statement that a certain property is true for all the elements of the domain. So we have the base case, and assuming the inductive hypothesis to be true, we derive the inductive step. Okay. And then we saw that why proof by induction is a valid proof mechanism. Then we started discussing about sets, relations, and functions. So um, we have various types of relations which we have defined, and relations are a very important entity in discrete mathematics as well as in computer science. We typically in the course deal with binary relations which are defined over two sets. Basically, it's a subset of Cartesian product of two sets, but we can also have the notion of n-ary relations. We saw various types of special relations like reflexive relations, symmetric relations, asymmetric relations, antisymmetric relations, transitive relations, equivalence relations. We saw various properties regarding uh, these relations. In the tutorial problems, we also counted how many number of relations of various forms we can have and so on. So we have a question here. Uh, okay, so thanks for your compliment. Yes, I always tried my level best to make the concepts as simple as possible. But of course, there are always a possibility of some errors, some typos, some linguistic errors while giving the lectures and so on. So please forgive me for those things. So since I am now talking about relations, let me take one of the questions asked by Devarshi Roy, a student who wants to know more about the closure property of a relation. So let me open it. Let me open the screen for you, and we want to discuss here the closure property. Okay. Of a relation R. Okay, so assume that relation R is over the set A. Okay, and assume that the set A has n number of elements. Okay, but whatever I am discussing here holds even if the set A has more than n elements. Now, since R is a relation over the set A, that means R is a subset of A cross A. Okay, it might have several ordered pairs from the set A cross A. Now, your relation R might be having some property. Okay, so let's say, for instance, we talk about the reflexive closure. Reflexive closure of a relation R. And let me make it more specific. Let me take a concrete example. So my set A has elements 1, 2, 3, and my set R is, say my relation R is say 1, 1 and 2, 2. Can I say relation R is reflexive? The answer is no. Relation R is not reflexive. Okay, why it is not reflexive? Because the ordered pair 3, 3 is not present in the relation R. Okay, so pictorially your relation R has the elements 1, 1, it has the element 2, 2. But if I ask the question, that is the relation R, if the relation R is reflexive, the answer is so. The answer is no, because 3, 3 is not there in the relation R. So now I want to get a bigger relation which has all the elements in my original relation R, and the bigger relation should have the reflexive property. Okay. Now that bigger relation, since I am allowed to add additional elements or additional ordered pairs to be more specific, I could add any number of ordered pairs as long as I ensure that, okay, whatever elements were there in the original relation, namely the ordered pair 1, 1 and 2, 2, they are still retained in the expanded relation, and the expanded relation is reflexive, I am fine. But I am interested here to do the expansion as little as possible, namely the reflexive closure here, reflexive closure of R will be the smallest possible superset of R which is also reflexive. Okay. So there can be several supersets of this relation R. Okay, so for instance, one superset could be that I just add the element ordered pair 3, 3. That could be one possibility. Let me call it R1. Another superset could be that apart from 3, 3, I also add, say, the ordered pair 1, 2. Another possible superset could be that I retain the ordered pairs which were there in R. I add 3, 3. I add 1, 2. I add 2, 1 as well. Okay. And like that, I can find multiple other supersets of relation R which are reflexive. Okay. But among all these supersets, I will be interested in the smallest possible smallest in the sense, in terms of the number of things that I have added extra. So it turns out that in this case, it's only the R1, the relation R1, which is the smallest superset of your relation R, because it has only one additional element, and that's the smallest thing which you have to, least amount of thing which you have to add to your original relation to make the old relation or the original relation a reflexive relation. Okay, so that's what we mean by closure. We want to close this relation R by some another relation S, and when I am closing it, I mean whatever were there in the original relation, whatever ordered pairs were there in the original relation, they are still present in the new relation, but I should not keep on unnecessarily adding redundant elements. I do not want to do that. I want to add only those many elements, least number of things, or the required number of things, so that the expanded thing becomes reflexive, because I am talking about here the reflexive closure. In the same way, if I'm talking about say the symmetric closure of a relation, symmetric closure of a relation R, then I'm basically asking the following: what tuples, what minimum number of tuples ordered pairs I should add to my relation R so that the new thing becomes a symmetric relation. And it turns out that if I just take the union of all the ordered pairs in my original relation R along with the tuples present in R inverse, where R inverse is basically just the reverse of all the ordered pairs which you have in the relation R. So if AB is present in the relation R, then PA will be present in R inverse. Okay. So you have your relation R. Suppose it has the elements 1, 2 and 2, 3. Now this relation is not symmetric because you have 1, 2 in the relation, but 2 is not related to 1. You have 2 related to 3, but 3 is not related to 2. But if I take the union of this relation with new ordered pairs, then I get a new thing, call it S. Okay, which not only have all the ordered pairs which were there in your old relation, but now the new thing is also symmetric. Well, there could be a possibility that you have a bigger superset as well, which not only have all the elements of your old relation, it's symmetric, plus it may have some arbitrary elements extra. Say this. So this relation S prime also have all the components, all the ordered pairs which were there in R. S prime is symmetric, but S prime is actually having redundant things which are not required to make your original relation R symmetric. That means you do not require the presence of 1, 1. You do not require the presence of 2, 2. So that's why this relation S prime won't be considered as a symmetric relation, right? So I hope I have answered your question, Devarshi. If you, okay, right, right. So now lots of questions have come up. So is this NPTEL course enough for covering the syllabus of GATE for discrete maths portion? As far as the syllabus is concerned, yes. But discrete maths is a topic where you have to practice lots of problems, then only you can get confidence in the topic. It's not that just by practicing the problems which we are covering in the course or which we are covering as part of our assignments, you will be able to solve each and every problem in GATE related to discrete maths. But as far as the concepts are concerned, topics are concerned, yes, I strongly believe it's sufficient to cover the topics which we have in the NPTEL course. Okay. Okay, so Alapan has already answered Priyanka's question. Thank you, Apan. So the questions which I had as part of the tutorial, they are the questions which I asked as part of the exams at IIIT Bangalore's discrete maths course. Okay, so all the questions which are there in the tutorials, They are basically the questions which I have asked over the last 5 to 6 years when I am offering the discrete maths course at IIIT Bangalore. Okay, and they are really challenging problem that really test the reasoning skills of the students and so on. Sorry, I cannot talk about spanning tree because that's not a topic of this course. Probably when we go to the graph, when we go to the module related to graphs, I can talk about trees, but spanning trees will be difficult to cover as part of this course. Okay. So the next live session, I'm not sure when it will be. We will plan it soon. Okay, so the solutions of the questions of the test, I think it will be better if we discuss them in the discussion forum instead of me directly posting the solution manual. I can always do that, but the whole purpose of having the discussion forum where you ask questions is that you discuss among your peers. Then only you will learn where you made the mistakes or whether your argument is correct or not, instead of I blindly going and giving the solutions to you. So that's why I'm purposely not giving you the solution manual. I can always do that, but that will lose the whole purpose. How mathematicians are convinced that their proofs are valid, there is no answer for that. Okay, there is always a case that many people believe that the proof is correct, and then later on people find a bug in the proof. Okay, so there is no precise answer whether your proof is correct or not. It's only through experience you will learn basically whether the proof is correct or not. You have to see whether you have used well-defined rules of logic to derive the statements in your proof, and then you will be convinced whether the proof is correct or not. In fact, you can search and you can find out examples of several cases of several well-known problems where people thought they have the proof, but the proof found out to be buggy later. The difficulty level of the NPTEL final paper will be similar to what we have for the assignments. So we will have 4 sections, and one section will be of type recall, where we will be having where there will be questions which ask you to verify certain definitions, certain properties. There will be one section based on questions which whose difficulty level will be similar to the assignment questions, and then there will be 2 sections where the questions will basically check the ability, the reasoning, thinking ability of the students. Okay, so I don't think the questions will be very difficult for the final paper. It will be relatively very easy compared to GATE or any other exam. And for your final grade, you have to pass. You have to score some certain number of marks both in your assignments as well as in your final exam paper. Okay. Right. So you can continue your questions here if you have any other questions. Okay. So is Devarshi Roy here? The discussion, yes, on the live session. I have already answered the question related to the closure property of a relation. Do let me know if that is clear or not, because that's the only question we got in the Google forum for this course. There is a good question. What's the use of discrete mathematics in cryptography? Um, so basically, whatever the proof strategies that we discuss in this course, direct proof, indirect proofs, they constitute part. They actually are very helpful when we try to prove certain things in cryptography. Then topics related to how you count certain things, topics related to properties of functions, what are the various types of functions. All these concepts play very important role in various topics in cryptography. Okay, so in cryptography also we encounter various kinds of functions. We like to analyze their properties. We also encounter various kind of sets. We also ask questions like how many ways adversary can do certain tasks, and if certain set has certain kind of properties, what can be the cardinality of that set. Questions like this, a question like these always are encountered in cryptography. Also, concepts from graph theory are very useful in cryptography. Okay. Uh, so Siddharth, for you, if you are understanding the question, so as I said earlier, discrete mathematics is a topic where you have to solve lots, practice lots of problems. Then only you can get a, you can feel confidence regarding specific topics. So the textbooks that we are following for the course, specifically the textbook by Alan Rosen, not Alan Rosen, sorry, Kenneth Rosen. That textbook has very nice practice problems, so I recommend to go through them. And apart from that, discrete mathematics is a topic where you can find lots of problems online as well. So you have to solve problems. Just watching the lectures and going through the tutorial problems and the assignment questions will not be sufficient. Okay, so you have to solve lots of practice, lots of problems. That's the only thing. That's the only thing I can recommend to you. Okay. Uh, there won't be any advanced course in discrete mathematics from my side in future. Maybe some faculty member from some other institute might offer it. But yes, that's a very nice question because there are always advanced topics in discrete mathematics. In fact, one can offer a whole course on combinatorics itself. But I will not be offering any advanced course on discrete mathematics in the future. Okay, so again, Sumit, to answer your question, practice, practice. Okay, so you have to practice the questions. It's not only those questions, related questions, questions from various books, and then only you will get a feel of how to approach a particular problem. There is no rule book which says that you have to approach a specific question only in this way and so on. Whether when a question, when someone asks you prove something, uh, there is no rule which says that okay, if you see a problem of this form, then you have to go for direct method, or otherwise you have to go for indirect method. Also, that comes only from experience. Okay, so whenever it comes to P implies Q statements of the form P implies Q, you only have two methods, either direct method or indirect method. Try first the direct method. If that does not work, then try to prove either using proof by contrapositive or proof by contradiction, because they are the two most popular approaches when it comes to indirect proof methods. Okay. Um, okay, Nita, what do you want to know about quantifiers? I didn't get your question. You just wrote here about quantifiers. So what exactly is the question? Uh, Prashnath, I will suggest to discuss it in the discussion forum. It will be difficult to get the question itself first and then recall the solution. But if you ask this question in the discussion forum, I will see whether someone respond to that, because I expect the participants to discuss the assignment questions during the discussion forum, in the discussion forum, but I'm not seeing that happening. Okay, so if if you please post a question in the discussion forum, I will see. And then if no one answers your question, I will help you to solve the problem. What exactly you want to know, the Nita, regarding the definition of quantifiers and types? Is the type of quantification not clear, or what exactly is the question? We have two types of quantifications. Universal quantification and existential quantification. Universal quantification basically is used when you want to say a statement to be, when you want to say a statement which holds, or when you want to say a property which holds for all the elements in your domain. Okay. So if I say, for instance, a property, all human beings require water and air to survive. So that's a universally quantified statement. Okay. But it's not the case that all human beings require meat to survive. Depending upon whether you're uh, vegetarian or not, the answer is yes or no. So that property that some people are there who require meat to survive holds only for non-vegetarian people. So that's existentially quantified statement. So depending upon what kind of property you want to assert, whether it holds for every element of your domain or whether it holds only for some element of the domain, we use universal quantification and existential quantification. Okay. So for instance, if I take the prime number as a property, primality as a property, so we know that we can't say that all prime numbers are odd, because we have an exception, namely the number 2. Even though it is a prime number, it's an even number. Okay, so that's why I can say a statement that there exists one even number which is prime. Okay, but not all the even numbers are prime, because I know that except 2, no other even number is a prime number, because you take any even number different from 2, it will be divisible by 2, right? So that's why, depending upon the type of property you want to assert, we use universal quantification and existential quantification. Intuition on partially ordered set versus totally ordered set. So partial ordered set means in the you have a relation over a set which is reflexive, antisymmetric, and transitive. Okay. Okay. So let me open the board and then we can discuss there. Okay. So partial ordering versus total ordering. First of all, partial ordering means your relation R is reflexive, antisymmetric, transitive, all three of them. Total ordering is also a relation over a set which is reflexive, antisymmetric, transitive. And what's the difference? The difference is the following. So this relation R is defined over a set, right? So it's a subset of S cross S. This relation is also over S cross S. Now in this relation, it might be possible that you have elements, say AB, which are member of S, and neither A is related to B nor B is related to A. That's quite possible, even though your relation is reflexive, antisymmetric, transitive. But when it comes to total ordering, it holds that you take any elements AB from the set S, either A is related to B or B is related to A. So that sense it's total ordering. That means you cannot find unrelated elements in the relation R. That's the right term. In if in the that's why the term partial and total. Partial ordering means you might have pair of elements A and B which are totally not related as per the relation R, even though your relation is reflexive, antisymmetric, transitive. Total ordering means you give me any elements AB from the set S, there will be some relation among them. Either A is related to B or B is related to A. Okay, so let me make it more concrete with an example. You take a set S to consist of elements say 1, 2, 3. Now take two relations. Okay, so yeah. Now both these relations R1 and R2 are reflexive, antisymmetric and transitive. Okay. Let me check. Yes, so both of them are reflexive, antisymmetric and they are transitive as well. But in R1 you have elements of the form you have the case that you have elements 1 and 2 in the relation S, but neither 1 is related to 2 nor 2 is related to 1. That means this relation R1 does not tells you what exactly is the relation among or what's the status among the elements 1 and 2, because neither 1 is related to 2 nor 2 is related to 1. So that's why R1 is an example of partial ordering. But if you take this relation R2, right? So it is reflexive, antisymmetric, transitive, and it's a total ordering because you take any pair of elements, say 1 and 2. So 1 is related to 2 here. You take 2, 3, 2 is related to 3 here. You take 3, 2, again 2 is related to 3 here. That means you do not find here a pair of elements which are not related or incomparable. There will be some relationship among every pair of elements that you take from the set S. So that's why your relation R2 is a total ordering. There is always a relation between every pair of elements. Okay, so that's what is the difference between partial ordering and total ordering. I hope I have answered your question. So I have given the example as well, Paras, and there were lots of examples in the lectures as well. Okay, the lecture we have seen several examples. In the lectures we have seen several examples of relations which are partial ordering but which are not total ordering. Okay, and if you compare it in terms of Hashi diagram, then you in partial ordering basically you will see that in the diagram you have two elements about related to which you can't find any relation, no edges, nothing of that sort. Okay, whereas in a total ordering you will always have a relationship between every pair of elements that you take, and the Hashi diagram for a total ordering will be like a straight line chain. ask questions, please. I'm here for another 5 to 10 minutes more. So, Harshit, your question has been already answered earlier. The content is sufficient for GATE. I'm covering all the topics which will be there in GATE, but whether you learn those contents, whether you learn those topics or not, depends upon how many problems you practice. Okay. Week 5 lecture pi star. Okay, so what was pi? Because I don't remember the lecture exactly. Or let me open my laptop and see what was which specific lecture in week 5. Week 4. Week 4, which specific lecture? Can you tell me, please? Week 4, which specific lecture? Because in week 4 we have lecture 16, 17, 18, 19. There are 4 lectures. It's related to which topic in week 4? Because there were several lectures in week 4. You can tell me the exact the topic of the lecture, then I can find out and tell you. The length of binary strings of finite length. Okay. I think it's in week 5, not week 4 anyway. So, yeah, so um, right. So consider only 2 symbols are there, 0 and 1. Okay. Then the question is, how many strings of length 0 can be formed? How many strings of length 1 can be formed? How many strings of length 2 can be formed? And in general, how many strings of length I can be formed? And you keep on doing this, right? That means basically you are just increasing the length of the strings by one more position. So you start with strings which have 0 characters. So we use a special symbol for strings with 0 characters. We call it epsilon, some books call it lambda, null string, and so on. Now how many strings of length 1 you can form? Using the symbols 0 and 1, you can form 2 strings. One string which is 0, another string which is 1. How many strings of length 2 you can form? Using the symbols 0 and 1, you can form 4 strings. Okay. How many strings of length I you can form? Well, you can form 2 to the power I such strings. how many strings of length I plus 1 you can form? 2 to the power I plus 1 such strings. Now what I am saying is you take the union of all these strings, that is your set pi star. So pi star has infinite number of elements, okay, and pi star can be written as union of all strings of length 0. So let me call it as pi 0, union of all strings of length 1, union of all strings of length 2, union of all strings of length I, union of all strings of length I plus 1, and so on. So it's a collection of infinite number of strings. So that's why the overall cardinality is infinite. But I can count the elements of pi star. Count in the sense I can relate that, okay, I can list down all the elements of this pi star. I can say that, okay, this is the first element of set pi star, this is the next element of pi star, this is the next element of pi star, and so on. That means I can say that, okay, I start with epsilon and then I list down all the strings of length 1, then I start and then I list all the strings of length 2, then I list down all the strings of length 3, and so on. So now this list is an infinite list because it will keep on going and going and going and going. But the thing is, it is countable in the sense you give me any string of any length, that will definitely appear somewhere here in the list, and I know where it will appear, because any string which you give from pi star, you give me any string x from pi star, it will have some length. Call the length as I, and if its length is I, that means definitely when I am listing the strings of length I here, I will encounter x. In that sense it is countable because I can enumerate, I can list down all the elements of the set pi star in an unambiguous fashion, okay, and I can list down it in such a way that you tell me any string x from the set pi star, I can show you where exactly it's going to appear in my order. Okay. Yeah. Right. So you have 2 more minutes. If you have anything else to ask, otherwise we always have the discussion forum. Okay. I regularly see the discussion forums and I reply only to the questions which make sense. People do ask certain questions which are very trivial and which are completely incorrect. So it's not possible to answer each and every question. And again I'm saying that the whole purpose of discussion forum is that the students discuss among themselves, the participants discuss among themselves. But that's not happening as of now. Okay, so let me stop here. I hope you enjoyed the session. I will be happy to take further questions in the discussion forum. Thank you.